Hey folks, why it was almost impossible to make blue LED. Light-emitting diodes, LEDs, are semiconductor devices that emit light when an electric current passes through them. The phenomenon responsible for this emission is electroluminescence, wherein electrons recombine with electron holes within the device, releasing energy in the form of photons. Historical context: the history of LED development dates back to the early 20th century, with the discovery of electroluminescence in certain semiconductor materials. The first practical LED was developed in the 1960s, primarily emitting red or infrared light. Green LEDs followed shortly thereafter, but the quest for blue LEDs proved to be significantly more challenging.
Semiconductor basics. To understand the challenges of blue LED development, it's crucial to grasp the fundamentals of semiconductor physics. Semiconductors are materials with electrical conductivity between that of conductors and insulators. They are characterized by their energy band structure, which determines their electrical and optical properties. Band theory and energy levels. In semiconductors, electrons occupy energy bands, with a valence band representing the highest occupied energy level and a conduction band representing the lowest unoccupied level. The energy gap between these bands, known as the band gap, determines the material's electrical conductivity and optical properties. Wavelength and color emission. The energy of photons emitted by an LED corresponds to the energy difference between the conduction and valence bands. Thus, the color of light emitted by an LED is determined by its band gap energy. Red LEDs typically have lower band gaps, while blue LEDs require higher band gaps due to the shorter wavelength of blue light.
Materials challenge. The primary obstacle in creating blue LEDs was finding a semiconductor material with a sufficient bandgap energy to emit blue light. Traditional semiconductor materials like silicon and gallium arsenide lack the necessary properties for blue emission. Researchers turned to compound semiconductors, such as gallium nitride (GaN), as potential candidates. Crystal growth. Growing high-quality GaN crystals was one of the most significant challenges in blue LED development. GaN has a hexagonal crystal structure and is notoriously difficult to grow in large, defect-free crystals. Various techniques were explored, including hydride vapor phase epitaxy (HVPE), metal organic chemical vapor deposition (MOCVD), and molecular beam epitaxy (MBE). Epitaxial growth. Epitaxy is the process of depositing thin crystalline layers on a substrate, with the crystal orientation and structure matching that of the substrate. Epitaxial growth of GaN layers on suitable substrates such as sapphire or silicon carbide required precise control over temperature, pressure, and gas composition to achieve uniform and high-quality films. Defect management. Dislocations, stacking faults, and other crystal defects were common in GaN films, negatively impacting LED performance. Researchers developed innovative techniques to reduce these defects, including buffer layers, strain engineering, and post-growth annealing processes. However, achieving defect-free GaN films remained a significant challenge. Material doping. Doping is the process of introducing impurities into a semiconductor to modify its electrical properties. Doping GaN with elements such as magnesium or silicon Si was crucial for controlling the material's conductivity and improving LED performance. However, doping GaN presented its own set of challenges, including dopant activation and diffusion. Efficiency enhancement. Early blue LEDs suffered from low efficiency and poor brightness compared to their red and green counterparts. Improving LED efficiency required optimizing device structures, electrode configurations, and packaging techniques. Surface treatments, passivation layers, and quantum well designs were also employed to minimize non-radiative recombination and enhance light extraction efficiency. Quantum mechanics. A thorough understanding of quantum mechanics was essential for optimizing LED performance. Quantum mechanical phenomena such as carrier confinement, tunneling, and quantum well effects played a crucial role in determining LED efficiency and spectral characteristics. Researchers utilized advanced quantum simulation techniques to design and analyze novel LED structures. Collaborative efforts. The quest for blue LEDs was a collaborative endeavor involving researchers, engineers, and industry stakeholders from around the world. Academic institutions, government agencies, and private companies contributed resources, expertise, and intellectual capital to advance LED technology. Collaborative research initiatives and consortia facilitated knowledge sharing and technological innovation. Breakthrough and impact. The breakthrough in blue LED technology came in the 1990s when Shuji Nakamura, Isamu Akasaki, and Hiroshi Amano successfully demonstrated high-brightness blue LEDs based on GaN materials. This breakthrough not only completed the RGB, red, green, blue color spectrum for LEDs, but also revolutionized various industries, including lighting, displays, and communications. Commercialization and applications. The commercialization of blue LEDs paved the way for numerous applications, ranging from energy-efficient lighting and full-color displays to optical storage and communication technologies. Blue LEDs enabled the development of white LEDs through phosphor conversion, offering a more efficient and durable alternative to traditional incandescent and fluorescent lighting. Nobel Prize recognition. In recognition of their pioneering contributions to blue LED technology, Shuji Nakamura, Isamu Akasaki, and Hiroshi Amano were awarded the Nobel Prize in Physics in 2014. The Nobel Committee highlighted the significance of their work in advancing energy-efficient lighting and its potential for addressing global energy and environmental challenges. Future directions. The evolution of LED technology continues, with ongoing research focused on improving efficiency, reliability, and versatility. Emerging trends include the development of micro-LEDs, flexible and transparent displays, and advanced lighting control systems. Nanomaterials, quantum dots, and organic LEDs, OLEDs, represent promising avenues for further innovation in lighting and display technologies.
Conclusion: the journey to develop blue LEDs epitomizes the spirit of scientific inquiry, technological innovation, and collaborative effort. Overcoming formidable challenges in materials science, crystal growth, device fabrication, and quantum physics, researchers transformed a seemingly impossible dream into a transformative reality, shaping the modern landscape of lighting, electronics, and communication. The legacy of blue LED pioneers continues to inspire future generations of scientists and engineers to push the boundaries of possibility and unlock new frontiers in science and technology. Subscribe to this channel. Our dedicated team promised to boost your understanding.